Thanks a lot, Tanisha, for that wonderful introduction. Hello, everyone. Hello, React Day. The last couple of talks have been pretty impressive, and I've been looking at all the set of talks and very excited for all the things that are there in store for all of you. So, so this talk is about concurrent React and 3D and sort of the great relationship that they share and how building things with 3D on the web is now better with the concurrent features that are in React 18. So let me start off with some history. I started playing around with 3D sometime last December, and my first dig at it was to create a box or a glowing cube of sorts. And this is now the logo of the internals meetup run by Suzat Shriyata, who is also a part of the front-end discussion panel that's happening later in the day. So hope you guys check that out as well. So now I was very intrigued with Blender in general, and so I wanted to see how I can take this knowledge of doing 3D and take that to something that I already know, which is building things on the web, right? But let's if you go at a first principles thinking sort of an approach, there are a lot of different things that like the fundamental components of the web are probably HTML, CSS, and JavaScript, right? But when it comes to a 3D scene, there are three important things, which is the mesh, light, and camera, right? And this is the understanding what these are fundamental to understanding 3D in general, and this is not specific to just on the web. If you are building, probably people are on game dev may understand this better. But if you're into a sort of any 3D tooling or anything that requires you to work with 3D, a fundamental understanding of all these three things are important, right? So lights and camera are probably something that you understand, but what is a mesh, right? So a mesh is basically two things, which is geometry and material. So what is geometry? Geometry is think of this as a plastic cube, a blue plastic cube, right? In this case, the cube is the geometry, and the blue plastic that you see is the material, right? So you could extend that for any 3D object in general, right? Let's go a level further below. Now, what is geometry? So this is might be a little bit mathy, but that's still okay. So in 3D, every point is a vertex, right? Every point is a vertex, and these vertices, connect to form triangles, right? Why is it a triangle? In 3D, it's called as a primitive. And why is it a triangle? Is because triangle is the most simplest primitive that you can take, and which cannot be further broken down into further shapes, right? So, and a triangle is always at 3 points, and a triangle has 3 points, and the 3 points will always be coplanar. I'm telling more math concepts here, but it's a coplanar. Think of it as given a simple plane that looks like this. It is always true that all of these points will lie on the same plane. But if you take a square, it has 4 points, and there is a chance that the fourth point can be on a different plane, right? So that is why most computer graphics or any computer graphics algorithm optimizes for building triangles, and that is why when you look at either Unreal Engine or any other game engine, when they show their performance benchmarks, they talk in terms of triangles. They say this can render this billion triangles in less X number of seconds, right? So that is why it is triangles, because it is the easiest for a computer graphics algorithm to work on. So when a light source, so now we know what vertices are, what are primitives. Now, when we take a light source and basically reflect on top of a primitive, that becomes a fragment, right? And this is what creates shadows and the depth of field, right? So, so these fragments are then rasterized. So the rasterization is a process of taking something that looks like a 3D vector graphic and turns that into a 2D image, right? So what we are seeing right now is pseudo 3D in a way, right? Because it's not, we are still looking through a 2D screen, which is your monitor, right? The depth of field comes only because of this rasterization process of creating this, and it's basically a trickery to the brain to convert what you see as 3D into 2D, right? So this is a little bit important to understand how depth of field works, how lighting impacts everything in your 3D space, right? Now, on the web, how do we do? So WebGL has been an API that has been available since forever, and it is based on OpenGL. OpenGL has been available since like 1992. It is, and WebGL is a JavaScript API that you can play around with today. And you can do, it's not just for 3D, it is for rendering high performance 3D and 2D graphics on the browser, right? And it's based on OpenGL ES 3.0, which is fairly latest, right? And so WebGL is the core API that most of the graphics apps or render like anything that requires graphics on the web use WebGL in some form or the other. There are other upcoming APIs like WebGPU, but that is beyond the scope of this talk. But new APIs are also coming in the future. So now let's see how we draw a simple triangle with WebGL, right? So this is a video. There is a reason why this is a video. So in a WebGL program, right? As I mentioned, it is a rasterization engine, and the whole a WebGL program always deals with three things. It deals with points, lines, and triangles, right? And for the WebGL, what WebGL does is it needs to run programs on top of your GPU, right? Your GPU, which is your graphics processing unit. And to run on top of a GPU, it needs to send a pair of two functions or two shaders specifically. One is called as the vertex shader, the other is called as the fragment shader, right? And a vertex shader, if you can think of, that is what you can see from line 4 to 9 is the vertex shader. And what you can see from line 11 to 18 is the fragment shader, right? In this piece of code, right? And the vertex shader defines what is called as the position of every fragment, of every fragment. So say, for example, if you say every vertex that we saw earlier, right, it needs to have a position. So, and for every the job of the vertex shader is to describe what that particular position is, right? And similarly, when it is computing this particular process, it also does another pass to identify what the color of that particular pixel should be, and that is actually given by the fragment shader. It defines RGBA colors. Here you can see it's RGBA, and this is the opacity, which is very similar to what we do, but instead of from 0 to 255, this is in a decimal sort of a thing, right? Okay, so now we know that we create a shader, we compile the shader, we do a bunch of things with the shader, and then we create a shader program. That's what you see here. We do an attach shader, we do attach shaders, and we link this program. This is the program that is actually going to get run on the GPU. But a particular important thing that you might have noted here is this is not JavaScript. All of this is not JavaScript. This is actually run, and this is in a language called GLSL, or I think it's a graphics library shader language. It's a syntax that is very similar to C++, right? And it's a very strictly typed programming language, which is something that we are not used to in JavaScript, right? So then we get the canvas, then we do a bunch of things. We have to pass in data and all that. But the problem here is, at least the problem here is that you cannot like we've written, say, like 100 lines of codes, around 100 lines of code over here, and even after that we are not able to finish even a single triangle. That's the amount of work that is required to draw a single triangle with WebGL, right? But there are new like 3JS is what helps takes out all of that hard work and does all of that internally. So it abstracts out the important parts here. So say, for example, we say to 3JS, draw me a triangle. It does all of what you see over here. It defines the vertices, it creates and compiles the shaders, it builds those programs from the shaders, creates buffers, makes the draw calls, and finally draws a triangle on the screen and passes all of this information to WebGL, right? So as you saw, that it is a lot of 3JS is doing a lot of the hard work, and what we are doing with 3JS is basically standing on top of the shoulders of giants. Basically, 3JS has been there for a while, and it has been 3JS has done some phenomenal work in terms of reducing the complexity of writing 2D and 3D graphics on the web, right? Now let's try to draw the same triangle with 3JS, right? Let's see how much code that takes, right? This is standard practice. We import the 3D library, we create a scene, right? If you remember the first slide, this is the scene. A scene is where all of the elements go in 3D, right? We set a background so that it looks nice. And we use primitives that are available in 3js. Here, for example, the primitive is a triangle, and we draw lines from we create a shape. The shape by default is empty, right? The shape does not have anything. Now we have to draw lines from vertices. Say for so here the line 2 that you see here is takes in x and y coordinates, and we draw a line from 0 to 10, 10 to minus 10, and 0 to minus 10, right? And then we create a geometry with that. So this creates that triangle, right? It's not just enough to create a triangle, but we also we need to create a geometry with that. As I mentioned, right? We basically need to create a mesh. And what we need to do create a mesh is geometry and materials, right? So we've created the geometry from the triangle, and now comes the material. We'll just create a normal material, which is there are different types of materials that come out of the box. There are materials that look like glass, for example. There are materials that look like metal. There are materials that look like cloth. There are materials that look like wood, right? So we'll take a normal material, and since we want, if in the future we want to work, make it flip or do through 3D stuff, we use it as a double-sided material, right? So that you have the coloring on both the sides, right? And then we initialize the mesh. As you can see, the mesh creates mesh takes in two values, two parameters as arguments, which is the geometry and the material that we used earlier, right? Now we need to set the camera. As you saw in the first couple of slides, that a camera is also an important part of a 3D, because the depth of field changes based on where you position your camera, right? So right now we are positioning the camera at the x and y are pointed to 0, and the z value is 60. So ideally what we should see is the triangle comes, so the camera is somewhat placed over here, and the object is here. So we should see the triangle as a 2D flat surface, right? And we look at it, and then we render it. So for the rendering, we initialize a WebGL renderer, and then we get the app element, and then we render. We call the renderer.render method. So what comes up is an element that sort of looks like this. I will later add slides, so links to this particular slide, but where you can actually play around with your code sandbox. And this is what so the same triangle, same right triangle that took 100 lines of code to do, we're able to do it in less than 30 lines, and that's with comments, right? So that is the powerful abstraction that 3js provides, right? We've done enough now. I think the whole talk was supposed to be 3D. We've just done triangles at this point. So let's just jump into building things in 3D, right? Like enough of 2D, let's just go and do 3D stuff, right? So this is a metaphorical portal that I'm taking you all into, jumping into 3D, right? Now let's draw a cube. I know it's a cube is probably the simplest shape that you want to draw in 3D, but again, coming from first principles thinking, without actually understanding how you draw a very basic shape in 3JS, a 3D shape in 3JS, it is difficult to understand further concepts or make bigger, better drawings, basically, right? Again, customary imports, set up the scene. Now we use a different thing. Now we use something called as a box geometry. If you remember, we used a shape earlier because it was a 2D shape, and we are using that to create a triangle. But 3JS has better primitives. Has much higher level primitives than a triangle. It has something called as a buffer geometry, which a buffer geometry is basically something that takes in an array of values. They say a buffer of values. Let's say 10, 10, 10 is a buffer of values, right? This is an array of values. In this case, buffer means just an array where you cannot do random access, right? A buffer is just an array where you cannot just randomly go position A, position B, position C. It has to be accessed sequentially. You pass that buffer of data into WebGL to 3JS, which then passes that same data into WebGL. That's what we saw earlier, right? So in this case, this primitive is a box geometry where it automatically says I need a cube of size of width, height, and depth 10, right? That's what 10, 10, 10 means. And then we are just centering it in the so that we can see it nicely in the center. This is also similar. They're passing the same exact material, same normal material that we are passing, right? And then we are creating a mesh, right? So once we create a mesh, and we also now here's a small difference that you should see here is the camera is set at a different angle. The Z is still 60, but if you see X and Y values are 10. That is because we need to move the camera a little bit away from the object so that we can see the object in a 3D depth of field sort of a way, right? Now again, this is exactly the same thing, which is where we take in, we initialize the WebGL renderer that comes out of the box from 3JS, and then we render it, and then we actually just render it. Now we can see we have a nice box, which looks very cute, right? Like it's a multicolored box right now. Now that is that. Let's add some more spice to it. Let's make it rotate. Like, what have we done here? So if you look at the code over here, so you can see that the render function has taken a request animation frame, and then it's calling itself. That is the first point to note. And then we are doing some other thing. We have taken this cube mesh from here, and there is a rotation.y property that we're doing. What is happening here? What is this magic that is happening here? So basically, a request animation frame is an API in the browser that that takes in a function that you want to run before the browser repaint. So every time you render, this is understanding the whole browser cycle. Is a talk on its own. But every time a browser repaints, if we pass a function in the render, it calls it once. And if you want this particular animation to happen multiple times, that is why this function is calling itself, right? So we want this to be an infinite loop of renders, right? So that is the request animation frame that takes in this render, and then it does a rotation. Every mesh has a bunch of different properties. It has position, color, and rotation is just one of them. And we want to rotate it in the y-axis. So we are rotating it in the y-axis by a very small value. That's why you see a very slow sort of a rotation. And this runs at a smooth 60 FPS because we are doing it in a request animation frame. In general, it is a recommendation to do any animations in a request animation frame callback. And this will be very important when you go into other abstractions, because request animation frames forms the basis of doing animations in the browser, right? So now we have a very nice triangle, but let's say we want to make a change around the geometry a bit, right? Let's use a different geometry. We have a rounded box now. So rounded box does not come out as an out-of-the-box primitive from 3JS, but it is present in the library. Nevertheless, it is present inside the examples folder. Now we have a nice looking rounded box that we saw in the earlier slides that we are able to now rotate, right? So I think this is so again, with 30 lines of code, 35 lines of code, we're able to get a 3D object, introduce depth of field, introduce have different lighting if we want, and also make it rotate and do animations on top of it. This is sort of what 3JS is capable of, and we are just barely scratching the surface of what 3JS can do, right? So that's the big question right now. We've written, if you saw all the code, all of that is imperative, right? And we are in a conference that we are supposed to talk only about React, right? Or talk mostly about React. So how do we do this? How do we write it declarative, right? And of course, we'll use React. That's the whole point of this talk, right? So this is now we are already at one level of abstraction, which is WebGL and 3JS. We're introducing one more level of abstraction, which is Reactive Fiber. So Reactive Fiber is built by the Poimandres open source collective. It is a bunch of good-hearted people doing some really good open source work and building the top class libraries that you can depend on for production. So just for example, the previous talk that you saw about Zustand was as a library built by the Poimandres community. It is and you can Zustand, Jotai, Valshio, Reactive Fiber, React Spring are all multiple libraries that the Poimandres community has built, right? Now going back to the same example of so what is Reactive Fiber? That is the core. That is probably the first question that comes up, right? Like, so if you want to compose a 3D scene with reusable, self-contained components that can also react to your state and are also readily interactive, but also can leverage the large ecosystem of React. That is what Reactive Fiber gives you, right? And Reactive Fiber inherently it does not participate in the rendering loop of 3JS. And what Reactive Fiber is powerful enough to do is take some of the scheduling capabilities of React by writing its own reconciler, right? So a reconciler to just if it rings a bell, it is basically the process, the algorithm that happens of comparing state and props to identify whether something needs to be re-rendered or not. I'm massively oversimplifying what a reconciliation algorithm does, but that is the gist of it, right? So Reactive Fiber writes its own reconciler. And because of its scheduling capabilities, Reactive Fiber can even outperform 3JS at scale And it is also pretty easy. It is very easy to write concise, maintainable, and functional code because of its declarative nature, and also because of the Poimandres ecosystem. It is much more dependable even in using it in production today, right? So now let's go back to the same example of building the cube, right? How do we build the same cube, draw the same cube with Reactive Fiber? Again, customer imports. We take React and React DOM. If you are not familiar with what's happening on line 2, that is how you should import React DOM from React 18, where you're supposed to do it on client. The reason is because if you saw some of the talks earlier in the day, you know that there is client-side rendering and server-side rendering, and React team is trying to bifurcate these two by sub-packages of such. So the React DOM is, you have to clearly mention that this DOM is for the client, right? And we import Canvas and UseFrame. These are imports that we will talk about in a couple of seconds, right? Now, this is the same mesh that we saw earlier, right? But there are a couple of things that are happening here. So we seem to be having a use frame hook, and we have a mesh which seems like a JSX component, and then it seems to have geometry and material. But if you've sort of taken a look at the talk from the last 20 minutes, this probably rings a bell. You can understand that a mesh takes in geometry and material, right? And that same knowledge can be transferred over here without needing you to rethink a lot of the concepts that you have learned in 3D, right? Let's see what this renders, and then we'll dive in deep into each of these, what happens in every line of this code, right? Now we are using the create route, which is the new route API that comes in React 18, and we are rendering it in the canvas. So canvas is the same HTML canvas that you see, but in Reactive Fiber, there are some other optimizations that they have done on top of the HTML5 canvas, but the underlying is, you can think of this as to be a one-to-one equivalent to the HTML canvas, inside which we are rendering the cube mesh. And as you can see, now it's the same cube, but we're also rotating it. Where are we rotating it? On this line, right? So this is this is the exact same code that we've written earlier, where we said the current rotation. Again, we are modifying the current rotation, and you can see that we have a rotating cube, but with even lesser lines of code. Now this is the entire app, and if you look at the actual cube itself, this is barely 6 lines of code, right? 6 to 7 lines of code. Let's look at that a little bit deeper. Let's take a much larger look at it, right? So the ref, I think ref everybody probably knows, but so the ref returns a mutable reference to an object. It is used mostly used it can be used for handling. If I have to be technically correct about using a ref, you can depend on a ref being consistent across renders. And the most common use case for a ref is to attach it to DOM elements so that you can to DOM nodes essentially, right? That's the use ref. Now let's look at the further other lines of code, which is the use frame. So if you remember the request animation frame that I told a couple of minutes back, right? So use frame is basically just a hook that is an abstraction around the request animation frame, and you can see here that the ref.current.rotation is basically the same as mesh.rotation, right? This is a one-to-one match of what is happening there, right? But so the use frame, so anything that happens in the use frame happens at 60 frames per second. So this is very important, because if you're wrapping something inside 60 frames per second inside a use frame, that is going to happen 60 times per second. And this is even more dangerous than a use effect, because that happens at every render. This happens at every it happens at every frame, right? That is why this is very important to make sure that you don't initialize new variables or do any expensive operations inside the use frame, and keep it very minimal of what you want to do inside a use frame. But it is mostly to run animations is what we'd use your use frame. But in general, anything that you want to do at a 60 fps consistently, if you want to do something at 60 fps, you would probably use the use frame hook, right? Now let's look at the mesh, right? This we didn't see the mesh, but this is exactly what Reactive Fiber does behind the scenes. When we initialize a mesh like this, it takes that and creates a new 3-dot-mesh, right? That's exactly what it does, right? And we also have a box buffer geometry, which is again the same as the buffer geometry that we saw there. But the important point here is the attach equals geometry, the attach prop that you see here. It helps. It helps Reactive Fiber tell 3JS that attach this particular element that we've initialized to this particular property. So you see the mesh.geometry, the key that you see there is what is getting translated from the attach prop. This is also similarly, it's the same thing with the material also. We create a material. Every time you call the JSX component, it initializes a new material and then attaches it to the mesh, right? So behind the scenes, along with what we've said, this is what it does, right? We saw that it creates a new scene, it instantiates its 3JS objects for every component, composes all of them to become a scene graph. So what's a scene graph? Scene graph is, if you can think of scene graph as just a tree of elements, of all the elements in the scene, right? If it's just a huge, like the DOM tree, right? Like you can draw parallels to this to the DOM tree, where the DOM tree is just a tree of all the elements in the document object model. A scene graph is the same thing, but in a 3D scene, right? That you can probably draw parallels to that. It also, but an important thing that if you saw in the earlier code is we will not set up a camera. That is because 3Fiber already sets up a perspective camera at a particular position for us. Right, and it also does the render loop. This is basically what you would see in any React app. This is calling the render loop that automatically renders to the scene. It also sets up pointer events, so you can, if you want to interact with it, it's does pointer events. The raycasting is sort of difficult to explain, but you can think of raycasting as a point of light that goes to every mesh and then comes back of sorts. That is again, I'm massively oversimplifying what raycasting is. There are huge studies on raycasting, and there's like a proper engineering paper in computer graphics about raycasting in general. So I'm just massively oversimplifying whatever raycasting is, right? And it also handles window resize. We do not have to specifically talk about window resize, right? It handles that. But wait, we didn't actually set up any lighting, right? We set up a cube, we saw a mesh, we saw a material, we saw camera, but we never talked about lighting, right? So that is this next part of the demo, where we will look at a code sandbox, where we will talk about where we will showcase this is the basic lighting and shadows and all that, right? So this is, if you can see this particular thing, we have two basic components, which is a cube, a plane, and a plane. That's all we have, and we are rendering that inside a canvas. An important prop here is to show the shadow. This is just basic camera positioning, right? So this is a very normal sort of a cube that has no limelight in its life, right? So let's bring some light into it. Let's put it in the spotlight, right? So if once we put it in the spotlight, you can see it's casting some really nice shadows on its right? So, but again, what is so, and you also see something called as the ambient light. So if you can think of ambient light as an ominous source of light, where it's available throughout and it shines light evenly across all directions. This is physically not possible today. Even the sun is actually a spotlight or a directional light, but over a large distance, right? So it is technically not possible to have an ambient light, but for all intents and purposes, the sun behaves like an ambient light for us in the morning, right? So that's what you can think of as an ambient light. And without an ambient light, you can see that the entire scene becomes very dark, right? And there is just this spotlight that is coming here. And just to play around a little bit, we can also cast a yellow light if you want, right? That's what, and you can see that the shadows also look realistic, right? And you can probably not see it in ambient light because the ambient light is so glaring that, but there is a yellow ray of light that is coming out here, right? So that's the lighting story. Is that all we can do with Reactive Fiber? Absolutely not. Reactive Fiber offers us a world of possibilities, right? Let's say now this is my favorite part of the demo, where we stage a 3D model on the web, but using a Ford Mustang. I'm a huge car nerd. I like to talk about cars, and especially cars like Ford Mustang they are sort of they are muscle cars and also sporty cars, right? So I want to stage them in a 3D model like they are in a showroom, right? This is what that looks like. Just a disclaimer, I did not build this model. This is from a website called Sketchfab, where you can get 3D models, CC0 models that you can use in your own work, and we can make that look really nice. So just a fun bit of trivia for anybody interested. The Ford Mustang is started in 1965 and is one of the most successful Ford nameplate cars out there in the US. And it's a very sporty car. This is the latest 6th series edition that you're seeing on the screen here, right? And just to go now, taking away all the attention from the beautiful looking red Mustang, let's just go to the code a little bit. So you can see the model we are doing using this hook called as use GLTF, right? Use GLTF is just a hook that takes in a GLB model, which can takes in a scenes, right? So this there is a lot of there are a lot of things happening behind the scenes to take this GLTF model. Just for understanding, GLTF is the file format for 3D models on the web. It is an open format. It's been there since the 90s, if I'm not wrong. And it's built by an open group called Kronos. And even Microsoft actually contributes to GLTF, if I'm not wrong. So it's an open standard, and GLB is just a binary format of it. GLTF is, think of it as a very large JSON that file that you cannot understand, right? Standard tools like Blender or Spline or anything that you take will output GLTF for you. And Sketchfab is just one of those sites where you can get GLTFs for free, right? That's what this is, and we are the same use frame that you saw before, and we are now rotating it in this direction, right? That's what we have done. Again, this is the color we're setting a black background color. You see a nice fog over here that happens in the horizon of sorts, right? And we're using a suspense here. Why are we using suspense? This is a concurrent feature. So suspense enables you to defer something to load without and you can set up a spinner or something like that as fallback. I think this is standard stuff. People have been using this in the form of concurrent mode since a couple of years, since like React 16. But since React 18, this is much more official. And so we are using a suspense. Right now, we are not using a fallback. And we are setting up the stage. This is where the lighting takes place. Let me show you a couple of lighting modes, right? Right now, this is in a warehouse sort of a lighting mode. You can see reflections, right? Let's say we want to show it in a dawn, right? When we want to show it in the early morning, you can see a very nice sort of a pink hue that comes up, and this is coming from the environment that is basically setting up all the lighting. It's basically setting up what behind the scenes, setting up multiple sources of lighting for you, right? And we have a nice this is the plane that you see in the black back underneath the car, right? This is very and this is just, again, this we are only still scratching the surface of what is possible with 3D. But I can imagine multiple things. If you want to showcase your product in 3D, this is probably a way to go. Using with React Fiber, in less than 30 lines of code, 33 lines of code, we are able to get a full-fledged GLTF model and show it on the web, right? And this is running side by side, right? This is not a and this is running in a code sandbox, right? Is that it? It's not like, but as web developers, we also want to see how we can blend HTML and 3D, right? Let's do that now. So this is another demo where we have a Hello World app. Again, these are all some tweaked examples coming from the Poimandres group itself, most of which I did not build. I'm just showcasing some of them with just minor tweaks, right? And this is a point set of stars, a set of stars that's sort of floating in the abyss, floating in space, right? And again, for all of this, there's a couple of things that are happening, right? Let's take a look at the index.js file. So all of the things that you see here, this text is actually just an overlay, and you can see that it's just a H1 tag, which is some inline styling, which you're not supposed to do, but I did anyway. So there's some inline styling that is happening over here, and that's basically all the text that is happening, right? And we are using the same create root API from React 18, and then rendering the overlay, right? That is done. What is in the background is what is more interesting, where in the canvas we are rendering the stars. I think I'm over time by a couple of minutes, but I'll quickly wrap this up. So it has this has points and point material. What are these points? Points is every point that you see here. And how do we so basically what we're using is we are using a random generator that generates a particular count of points in a sphere, right? So this is the sphere that generates. So basically, this generates an array of values that have different positions, right? And those positions are passed on to these points. This is an instance of multiple points, right? This is what is called instancing, where you have a single instance of a position, and we are of a material, which in our case the material is that small circle that you see here. If it's too small, let's just make it a little bit too big. That's a little bit too big, right? Yeah. Let's make it cuter. Yeah. So the big circles that you see is the point material, and these points render around 5,000 stars. So we can tweak that. We can make it 100 stars if you want. We can make it lesser number of stars. That's all up to what we decide we want to do, right? So that's another way of using 3D. But now let's talk a little bit about what is possible, what are the realms of possibility with React 18 and some of the concurrent features in React 18. Right. Specifically, we'll talk about one API, which is the start transition API. In the morning, you probably heard about this, but I'm just recapping this a little bit. So you can mark state updates as transitions, which allow React to prioritize necessary state updates. So you can say what is important to React, it will prioritize only that, and everything that is non-urgent, it will just interrupt until we have an urgent update like a click or a key press, right? A typical scenario today is we'd use the debouncing or throttling for many of these scenarios, but they can potentially be replaced by start transition. And this is what the API looks like a little bit like. So say, for example, if you have a search box, the set input, if a setting state, the set input value is what the value of the input, that is urgent. Why is it urgent? Is because every time you type, you need to show a state update. You need to save it in your React state, and then that has to show up immediately, right? That is why that is an urgent update. But for example, if you have to search, we don't have to immediately search. This is basically what you do use debouncing for. You would wait for 30 seconds or something like that and trigger off a call to your API, right? But instead, if you use a start transition, you can set the search query of the input. So this is just trying to understand what the start transition API does. Next, I'll sort of show a video. It's a video recording from Paul Henshin of what is possible with it. So this is here you can see that this is an object that is turning, and behind this in the camera, behind this particular object that you can see, there are around 510 text geometries that are created in runtime, right? And this is extremely tasking for the browser to do. Sometimes the entire app will freeze, and if you're running it on a code sandbox, it will probably shut down, right? And it is possible that if you're running it even on an Apple M1, this will still make it slow, right? So but with React 18, right? Here you can see that this takes around 15 FPS if you saw that earlier. Right, but just by introducing the start transition API over here, as you can see, so this is where you can see that each block that you are seeing on line 14 to line 18 is where the block of text that you saw in the background was getting generated, and this is just random characters that are getting generated dynamically during every render, right? So now with since we have wrapped that inside a start transition, those updates are getting deferred, and you can see that you're still hitting 60 FPS. Something that with vanilla 3JS that took 15 FPS, we are easily able to hit 60 FPS just by introducing the start transition API. That's sort of the end of the talk. And with React 8, it is now possible to go beyond the current standards of performance, and there is a chance of truly competing with native development. We've looked at how transition APIs are able to enable us to time slice, and they can potentially defer heavy tasks. They can render a large set of meshes if they want, and how Reactive Fiber is also it brings the best of both worlds of React and 3JS together. Right. Before I leave, I want to show some real-world examples of what people have built with React Fiber. So Sogan is a web-first metaverse where this is entirely powered by React Fiber. It's a proper full-fledged metaverse experience that is running in the browser. You might see some lags because of screen sharing and everything, but you can probably go around and play with this entire thing on your browser today. And all of this is done by some of the core members of Poimandres, some of the people who are behind React Fiber, right? And then a final shout out to their docs. It's docs.poimandres / React Fiber. This is where you can find all of their documentation. That's the end of it, and I'll probably hang out for in the session for any other questions. Thanks, everyone.